suppose there's a slide there that's just showing you, setting it up. You're going from moles to grams or grams to moles. There's a slide just kind of showing you there's a mole of copper, there's a mole of oxygen, about the size of a basketball. 1 mole of oxygen is about 22.4 liters of oxygen. It's about a little bigger than a basketball. Calcium carbonate, water, 18.02 grams or 18.02 milliliters of water is a mole of water. Okay, the chemical equation. So I think I'm going to just get myself some blank space here. A lot of times I draw this out on the board. Not sure which is best, but if I do it right here, it's captured. The chemical equation. So let me introduce you to it. Let's pretend for a moment that you work for Alcoa. And what does Alcoa make? Alcoa is the Aluminum Company of America. That's where they got that name. Aluminum Company of America. What do they make? They make aluminum. How do they make aluminum? Well, someone somewhere digs bauxite. They go find bauxite, and they dig bauxite out of the ground, and that is aluminum that has been oxidized. Aluminum metal, I mean, this looks like it's pretty durable, but you throw this in a landfill and come back in 100 years, and what you're going to find is Al2O3. A little acid, little condition, it's going to oxidize. But they're not interested in that. They're interested in aluminum, elemental aluminum. That's what that is. That's what they sell. So what they do is they take bauxite, they react it with carbon, and the carbon combines with the oxygen and form the oxygen that's in your bauxite and forms carbon dioxide. The carbon dioxide is gas. It releases, and what you end up in a big, huge, hot cauldron is molten aluminum. And then they pour it out into bars or sheets or foil or whatever they want to make out of it. Follow me? This is a chemical reaction. Okay, number one. So what we have here is we have the reactants, and over here we have the products. So we're typically showing the progress of a reaction. Here's where we're starting. Here's where we're ending up. These are the products of the reaction. The other very important thing in a chemical equation is to make sure that you represent the reactants and the products with their proper chemical formulas. Aluminum oxide is Al2O3. You remember that. Aluminum oxide, positive 3 charge, minus 2 charge. And you come down to that is the correct formula. So we wouldn't write this chemical equation with ALO or Al2O2 or Al3O4 or whatever. It's this. This is aluminum oxide. Once we get the chemical equation with the proper formulas, we don't change it. We don't change the formulas. What's entering into this reaction is elemental carbon. So they take carbon or coke. This is coal that they've kind of heated up and gotten everything off of it except the carbon. And they grind it up and put it in here. So that's elemental carbon. This is elemental aluminum. This is carbon dioxide, CO2. Now, one thing that you will see sometimes in these formulas, in these chemical equations, is you'll see little subscripts after this stuff. I'm going to put these on here, then I think, I could erase them. I don't have to erase them, but I might. I put the wrong one there. This is the whole point of it. This is a G. So you see these little subscripts, and what the subscripts are telling you are various things. An S means it's a solid when at room temperature. The aluminum is going to come out of this reaction liquid at very high temperatures. But you cool it down to room temperature and it's going to be a solid. So we don't really worry too much about what it is at the end of this reaction, but what is it at 25 degrees centigrade? What is the physical state of the material? So carbon dioxide is a gas. Water, you might see an L after it. H2O is a liquid. You might see this, AQ. Anybody know what that means? Is what? Aqueous. Let me give you an example of that one. You might see this in a chemical reaction, NaCl, solid. What's that mean? White crystals. Or you might see NaCl, aqueous. What that's talking about is salt water. The salt has been dissolved in water. This is how it's being introduced into the reaction as an aqueous solution of sodium chloride. I'm trying to think what others. There's a few other subscripts. I always get to this point and I forget what the other ones are. Those are the most common ones. Solid, liquid, gas, aqueous, solution. Okay? Should have written those a little further over. Okay, let's go back to our equation. Okay, now we want to balance this chemical equation. We want to balance it. And what does balancing mean? We want to have the same amount of every element on both sides of the equation. And let's see if it is balanced. I've got one carbon here and I've got one carbon here. Balanced. I've got two aluminums represented here and I only have one aluminum coming out over here. Not balanced. I have three oxygens and I have two oxygens. So my aluminum and my oxygen are out of balance. I don't have the same amounts coming out. And why are we balancing it? There's a fundamental law that's behind this, the law of conservation of mass and energy in a chemical reaction like this. Nothing is created or destroyed. Not one single little nanogram is lost anywhere. Every single gram of material that goes in here comes out of here. In a different form, yes, but still comes out. The aluminum is coming out as aluminum metal. Didn't go in that way, but that's the way it's coming out. You follow me? Okay, so now balancing it, there'd be a couple ways to look at this. I mean, I could put a 2 right there, and that would balance my aluminum, but my oxygen is still out of whack, right? An equation like this, I'm going to attack the oxygen first. Now, balancing it, let me tell you one thing you can't do. You cannot change these formulas. I mean, if I said, oh, well, maybe it's CO3, Okay? That would get my oxygen all balanced. I could change the formula. Can't do that. The product coming out of here is not CO3, it's CO2. CO3 is not a product. CO3 is a polyatomic ion, carbonate ion. That's not what comes out of this equation. It's carbon dioxide gas comes out of this equation. But that would be really convenient if I could change the formulas, but you can't do that. All right, so what you can do is you can add coefficients. You can add coefficients on here. You can have more than one CO2 come out of here. So what is a common number of oxygens that you could imagine on both sides of this equation? 6. 6. So how would I get 6 oxygens over here? Okay, if I put a 2 right here as a coefficient, what I'm really saying is there are 2 of these. 2. So that gives me 6 oxygens, right? So how do I get 6 oxygens coming out in the products? Put a 3 in front of here. And that's really saying I've got 3 carbon dioxide molecules coming out of there. 2, 4, 6 oxygens. Perfect. Well, not perfect, but it's definitely down the right track. Okay, now, what do we have to do now? What's still out of whack? The carbon. So how many carbons? Put a 3 right there. That gives me the 3 carbons. And what finally? What in front of the aluminum? 4. Okay? All right, and now it's balanced. At the molecular level, we could say 2 Al2O3 formula units reacts with 3 carbon atoms to form 4 aluminum atoms and 3 carbon dioxide molecules. We could say that. But if we multiplied all of that by Avogadro's number, we wouldn't be talking about 3 carbon atoms, we'd be talking about 3 moles of carbon atoms. You see that? And that is the way we talk about it. What this really is saying is that 2 moles of aluminum oxide will react with 3 moles of carbon to produce 4 moles of aluminum and 3 moles of carbon dioxide. That's the way to read that. We got a balanced chemical equation, and now it is telling us on a mole-to-mole level how many moles of carbon dioxide are going to be produced from 2 moles of aluminum oxide. We're going to produce 3 moles. So, for example, you could have things like this. You got a ratio of 2 moles of aluminum oxide per 3 moles of carbon dioxide. Or let's put it over here. There are 2 moles of aluminum oxide reacts for every 4 moles of aluminum that you produce. Or vice versa, you could say you get 4 moles of aluminum for every 2 moles of aluminum oxide. Okay, so I mean here I'm using it one way. I got aluminum oxide on the top and moles of aluminum on the bottom. Here I've got it just the other way around. It's the same. That's the ratio. That's the ratio of moles of aluminum to moles of aluminum oxide. There's your ratio of moles of aluminum oxide to moles of aluminum. All right, could compare any two of these with each other, just based on these coefficients. So let's go one step further. Let's ask this question. How many moles of aluminum will be produced from the reaction of 12.9 moles of aluminum oxide? See, everything, I'm like a salesman who's selling, never been a salesman. I'm a salesman who's selling dimensional analysis. Just keep giving you examples. So here's our given. We got 12.9 moles of aluminum oxide. And I want to know moles of aluminum. That's what I said. How many moles of aluminum? That's the question. So based on my balanced chemical equation, I need a ratio here that has moles. What's going to be in the denominator? Moles of what? Aluminum oxide. Look, we got moles of aluminum oxide in the numerator. I want to convert to moles of aluminum. So I got to put moles of aluminum oxide down here and moles of aluminum up here. And then what do I do to get those numbers? I jump right up to my balanced chemical equation, and I see that I have a 4 in front of the aluminum, and I have a 2 in front of the aluminum oxide. The ratio is 4 moles of aluminum for every 2 moles of aluminum oxide. This is crossing out, and I'm converting it to moles of aluminum. And so what I find there is that 12.9 moles of aluminum oxide is going to produce 25.8 moles of aluminum. 12.9 moles of aluminum oxide will produce 25.8 moles of aluminum metal. You know, that's what Alcoa, I said, pretend you're working at Alcoa. That's what they want to know. Okay. Trying to think where to go from here. Yeah, we just now balanced our first chemical equation. I think what I'll do is I'll have us dig into balancing chemical equations on Thursday. I tell you what, if you are itching to play around with it a little bit, here are some. You can see the one we did. The one we did is right at the top, and then there's about 5 or 6 others you can play around with if you like. Whether I get back to this worksheet or not, you can always ask me. How do you balance it? What's the answer? But we will do a lot more with balancing equations then we'll go, where we're going to go from there is chemical, we're going to go to mass calculations based on this. Know that kind of where we're going is, here we got a pretty straightforward question. How many moles of aluminum can you produce from 12.9 moles of aluminum oxide? Imagine the question. This is what the question will ultimately be. How many grams of aluminum can you produce from 595 grams of aluminum oxide? We're going to be starting with mass of aluminum oxide and converting over to mass of aluminum, or mass of carbon dioxide, or how many grams of carbon are needed to react with it. We're going to go from mass to mass in these chemical equations. But this is fundamental to know how you balance it, what it means, and then how you use those ratios. Okay? So I think I'll tax your brains that much this morning. How's that sound? Now, some of you came in late. I took attendance, so you're going to need to